In the previous slide, we just saw that RNNs are good in capturing the context. Now, what is the importance of this context? Let's try to understand with a simple example here. Let's say we've the word which you're trying to predict is happy birthday, okay? And we're trying to predict, and this prediction is about every character is being predicted. That means, say you give one character at a time. Say, for example, you give the first letter H, and for it, once we give the letter H, then the RNN predicts the next letter after H, which is A, and then you give the predicted word as the next input, and you get P, and so on. So that's the character predictions, or predicting the characters. Now let's forget that there is nothing called context here. For a moment, let's forget that there is nothing called context. Now what happens is, say you've already predicted all these words from you've given H, and then you went on to predict A, P, P, Y, etc., and then now you've reached B. Now if the context is not there, what happens is, once you give B as the next letter, then the predictions would look for without the context, it look for say the words, the most frequent words which starts with B, and then look for those words, and then tries to predict the next letter after B. So, for example, the most frequent word starting with B is baby, and then so after B, without a context, probably you would get a letter which is predicted, which is A, which is that's the second letter of baby. Now, so this is probably what happens when the context is not there. Now let's look at how that context helps it. If we know that all those letters which were preceding before B were H, A, P, P, Y, then we look at, okay, you have these letters which has been already been all these letters which were before B are happy, and then you look at, okay, provided these letters, or condition on these letters which are happy and B, what is the next probable letter? So given that you have seen the letters happy and B, then the next probable word could either be I, which is the second word for birthday. So that's the importance of context. And then RNNs, or any of these RNNs, are good at understanding the context. So how does it try to get these contexts? Now let's look at the overall structure of these RNNs. So you have an input, and you have something called hidden state, and this hidden state is called the cell state, and this is what stores the context. Let's in the first timestamp, that is the first letter, you input your letter H, and you have initial cell state which comes here. It's unfortunately it's not represented here, but there is one initial cell state which is there, which could be, say, a random initialization here, and based on that you predict the next letter, which is A. And then this next letter becomes your input in the second time step. Now what happens when you go into the second time step is, you have already learned the context here that the first letter was H, and this gets transmitted here. So this the context of the first letter, which is H, along with the next input A, together forms the overall context to give you the predictions of the next letter P. And then if you go to the third step, you have the context of both H and A, wherein you predict the next and the third input, which is P, to predict the next letter P, and it goes on like this. So that's how the context is learned, and with this unit called the cell state, which keeps on transmitting from one time step to the other. Now one characteristics of LSTM is it has got its weights shared across different time steps. Unlike say a multi-layer perceptron, it doesn't where you have weights for each of these cell state, or not cell states. Each of these neurons, you have a certain kind of weight, but here the weights are shared across this. And this is and all these things, the cell state and transmitting the to the right, it's what helps in learning the context. But there are certain problems with RNNs, vanilla RNNs. What happens is, say, suppose this lengths become so big now, and when you have a lot of a lot of lengths, and if the length is so, the sequence becomes so big. Now the contributions of those letters which happens at the early stages diminishes and becomes very small. The other problem is, you have, during back propagation, you propagate backside. You have you get your loss functions here, and it gets propagated from the right to the left. And when the sequence becomes larger and larger, the gradients become smaller and smaller, and to a point that it kind of becomes so small that it kind of vanishes, or it becomes too small. And when that happens, the learning also kind of saturates, or learning kind of diminishes. Similar to, so that's called a vanishing gradient problem. And sometimes the reverse of it happens. So when you pass on from the right to the left, probably the gradients becomes greater and greater. That is, during back propagation, you obviously calculate the gradients, and it becomes greater and greater, and where it becomes too large, and there also it's called the learning ceases, and this is called the exploding gradient problem. So these two problems, in LSTMs, or sorry, in RNNs, are one of the greatest problems. So it usually doesn't work well for long sequences, and that's where LSTMs comes into play. LSTM is short form for long short-term memory. So what it happens is, it has got a completely different kind of architecture which is there. So you have every cell, or every LSTM units has got three type of inputs. The one is obviously the real inputs. The other is called the hidden state, which transmit from the previous LSTM unit, and also has got the cell state. Now the way LSTM works is, it has got three gates. One is the forget gate, one is the update gate, and one is the output gate. And then this is the output gate. And together with working all these gates together, tries to capture or capture the context, wherein only what is required is maintained, and what is not required is forgotten and eliminated, so that you capture the right context of what is required, and then pass it on to the one cell to the other. And that's way many of these problems, like your vanishing gradient problem and exploding gradient problems, get solved in an LSTM. We'll be dealing in depth with LSTM in the future videos, but this is just to give you a motivation of what is the importance of LSTM. So in this whole series, we'll be using our LSTM to create or to build our machine learning machine translation applications, and we'll see in detail about LSTMs in the subsequent videos. Now the other things which is important is the way for each using LSTMs, there are different types of architecture which can be used using these LSTMs, and these architectures varies in terms of the kind of problem statement we are trying to learn. So let's see these different types of architecture which comes into play, which can be used using LSTMs for different types of business problems we are trying to solve. So there are different types of architectures which are for using LSTMs, which can be applied for different use cases. Now let's look at the first one. First one is called the many-to-one architecture. This means that you have different inputs which happens, and based on the different inputs, you predict one one outcome. These things, these kind of architecture is really helpful for say use cases like your predicting a sentiment, say based on different words like I feel great today. These are different sequences of words based on which you predict that okay, this sentiment is happiness. The other one important kind of architecture is called the one-to-many architecture. Herein you give one input, and for that you get different outputs. So this is the kind of architecture which could be good for image captioning. So in an image captioning kind of use case, you give an image as a input, and for those image you give a certain amount of words which describes or captions the image. So in this case, there's a picture of a girl who is playing tennis, and the captions are a girl playing tennis. So that's useful for use cases like image captioning. And now getting into the architecture which would be used by use cases like your machine translation is called many-to-many architecture. This is also called encoder-decoder architecture. So here you have a certain sequence of inputs, and for those sequence of inputs you have another sequence of outputs, and that's why many-to-many kind of architecture. So here when you have a German equivalent of how are you, which have got 4 words, and then you predict the English equivalent, which is called how are you. So this is also called encoder decoder architecture. That is the encode. You see, the first part is the encoder part, which encodes the different inputs which comes into it, and based on, and then the second part is called the decoder. So the decoder kind of decodes the inputs and then predicts what could be the outcomes, or say so in this case, what is the translated or the target language which needs to be translated. So that's the many-to-many architecture. So we'll be using the many architecture in our application. So we'll in the next slide, what we will do is we will go into depth in the LSTM, in the overall architecture, the encoder-decoder architecture, and we'll get into some of the mathematical dynamics behind an LSTM unit. You will see what is a forward propagation, and what kind of how is the backward propagation works, and this in the overall context, and then understand how these things comes into play in our machine translation applications. So thanks for watching, and then we will in the next video we will deal with the mathematical details of LSTMs.